Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Oh, look, over here, the beams of light come together at a single point. This is called the focal point. Now, what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well, then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Ha! Thanks for joining me on Consider the Following.
Coming soon from Photon Pictures. In the Old West, things were different. In the Old West, straight-shooting ruffians ruled.
I'm as straight shooting as light is. No, you ain't. I'm as straight shooting as the light is. Or not. And two, or not.
Photon Pictures presents Lights Out at the IC Corral, a place where straight shooters ruled until she came to town.
Try your beam.
Don't miss Lights Out at the IC Corral. Coming soon at the speed of light through a projector in a quasi-multiplex mini-mall conglomeration near you.
The way a lens is curved affects how it bends light. See, the light from this candle is going straight into this lens. But because the sides of the lens are curved, the light gets bent. So look, down here we have a blurry patch of light. So I move the screen in. Right here, at this point, that's where the candle flame is in focus. But look, it's upside down. It's all caused by the sides of the lens being curved. Now, if a lens is curved in like this, we say it's concave. Now, concave lenses make things look smaller and farther away, like they're in a cave. Okay? Okay? Ha! Now, if the sides of the lens are curved out like this, we say it's convex. Convex lenses make caves look bigger.
Huh?
Hold on, I messed that up. They make things look bigger. That's right. That's it. The convex lenses, where the sides get bigger, they make things look bigger. That's it. That's what it is. Now, you have convex lenses with you all the time. They're right here in your eyes. Ooh. Anyway, convex, concave. Like a cave, like a...
Like a vex?
Sandy said he could always remember concave by thinking of a sort of a cave, hollow. Convex is the other way.
When we see objects in a mirror, we're looking at light that's bouncing off the object, then bouncing off the mirror, and then coming into our eyes. Here's the thing. Parts of the object that are on the object's right stay on the right. Parts of the object that are on the object's left stay on the left. It's a mirror image, for crying out loud. See, we're facing the reflection, not the object. So that's why we have ecnolibness. Ecnolibness.
You light a beam, you aim a mirror, you take them both, and there you have the facts of light. The facts of light.
Hey, Chitty, this is my makeup mirror.
We're using it. Joe and I are using it to conduct a light experiment.
Yeah. By aiming this laser we just happen to have in our dorm room at your overused flat makeup mirror, we're showing how light travels in a straight line, unless it's so bent, absorbed, or in this case, bounced off something reflective.
So lighten up, Blair. We're just about done. And we gotta go eat now anyway.
Oh, yeah? What are we gonna eat?
We're just gonna have a light lunch.
Stop that! When light bounces off of a flat mirror, it bounces off at the same angle that it hits. In fact, that's what light does with any mirror. But if the mirror is curved, it's making a slightly different angle with the mirror at different places. So it looks weird. Like, totally weird, man. Like, you could, like,
totally freak out. Whoa!
Hi, I'm Penn, and this is my partner, Teller. We're Penn and Teller. Did you ever, I don't know, look at yourself in a spoon? Well, if you look at yourself this way, you're right side up. But if you look at yourself this way, you flip upside down. Why is that? Well, let's look at the spoon sideways. See, the upside down way, the light waves come in, bounce, and cross themselves, making you look upside down. See? Whoa, 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 whoa.
See that can? Right there on the bottom. I'm going to reach for it with this grabber arm of science. But watch what happens. As I aim for the can and squeeze, I miss. Now, I'm really trying to get it. Here's what's going on. The light bouncing off the can is changing directions as it goes through the surface of the water. And so the can looks like it's in a slightly different position than it really is. And I miss. But if I compensate for the refraction of light, I can probably get it. I'm going to aim a little lower. Got it. You want some?
Here's a light trick that doesn't need mirrors. Put a penny in a pie pan. Now move back so you don't see the penny. Don't move, because I'm going to pour the water in. It's okay if you make a mess. Pretty cool, eh? See, light's always bouncing off the penny. But when you pour the water in, it makes the light bend. And the bending of the light makes the penny reappear. But the penny didn't move through all of this. But don't take my word for it. Try it.
When light hits something, it can be bent, bounced, or absorbed. Am I scary? Am I scaring you now?
Not particularly, no.
Huh? Huh?
Clearer than a corner office window. More focused than an automatic camera. Able to read fine print with a single glance. It's Lindo Lens. Disguised as mild-mannered bank teller, Stephanie Astigmatism, Linda uses a variety of concave lenses to bend light entering her eyes whenever things get blurry. Lindo Lens, defender of sight, focus, and the 2020 way. Today's episode, Hocus Pocus.
Try this. Get a glass of water and a pencil. Stick one end of the pencil below the surface of the water. And look, the other end disappears. You can only see the end of the pencil that's underwater. That's because the light is bouncing off the bottom surface of the water. It's what we call internal reflection. It's reflection inside. The same thing happens in this plastic rod. I'll shine the small laser in one end. Watch. Most of the laser light stays in the rod and doesn't come out till it gets to the other end, see? Pretty cool. Anyway, this is called an optical fiber. And that's how modern telephone calls and computer information are sent all over the world. The telephone call or the computer information is changed into a beam of light, sent down an optical fiber, and then decoded at the other end. Oh, excuse me. Hello?
Billy boy?
Oh, it's my mom. You guys go ahead. I'll catch up with it.
I'm Carol Tights, and I'm an orthopedic surgeon, and I'm just about to do some surgery on somebody's knee.
I believe I've heard it playing basketball. Tore the medial meniscus cartilage in my knee. They're going to snip out the bad cartilage.
Well, actually, when I was training, I trained to cut the knee open to do what we're going to do today. And then since then, they've developed the fiber optics, and we've been able to look inside the knee without cutting the knee open. This is the lens of the arthroscope, and the camera will go right onto the scope like so. And now all the images are going to be up on a TV screen. Bill, that's your kneecap up top, that white thing. Yeah, normally I don't think you could look inside of the knee. It would probably be fairly dark, but we've got this incredibly bright light coming into the knee through the miracle of fiber optics. And that's what's making the inside of the knee so it looks so bright and white and allows us to put it on video Let's get a still of that. We usually take stills and he'll give them to Bill when we're done. So he has them for his Christmas cards next year.
It's actually a pretty neat experience, except for having to pay for it, I guess.
Let's look at internal reflection in the light box of science. See, the light beam is coming into the box and hitting this mirror. As I rotate the mirror, the beam starts to bounce off the surface of the water until there, look, internal reflection. It's pretty cool.
Want to see light bend? Watch. Take an empty soup can and poke a hole in the bottom. Be really careful or have an adult do it for you. Put your finger over the hole and fill the can with water. Now put a flashlight over the top and turn off the light. Take your finger off the hole and look. You can only see light where the water hits. The light stays inside the water. And when the water bends, the light bends too. Science.
It's hot. It's hot enough to grow cacti. That's because this is a greenhouse. It's a building made of glass. And glass acts a little bit like a mirror. See, all different kinds of light energy beam down from space on top of the greenhouse. The glass reflects the short wavelength ultraviolet back off into space. The long wavelength infrared, the heat, gets trapped inside, and it gets hot. Visible light, the light that we can see, goes right through the glass, and it hits the green plants. The plants use the visible light to help them make food. Now, while they're at it, they give off heat. That's infrared light, and that's trapped by the glass. And that's what's keeping it warm in here. It's not warm in here, it's hot. It's hot in here. It's like 33 degrees Celsius. I mean, we're growing cacti in here, for crying out loud. It's a greenhouse. Light travels in straight lines, right? Everywhere on Earth. But a famous scientist named Albert Einstein discovered a famous equation. You may have heard of it. E equals mc squared.
What?
And what that means is there's some relationship between E, that's energy, and mass, that's m. So everything that has mass, that's you and me, our home planet, the Earth, and things like stars, like our own sun, all those things have gravity. They have mass. Now, Einstein predicted that things that have gravity could make light bend ever so slightly. Wouldn't go in a straight line anymore. And sure enough, using a very powerful telescope, scientists have looked at huge stars deep, deep, deep in space. And they found that light can be bent into these wild patterns. Kind of like the patterns you see when you look through a kaleidoscope. Oh, man, that's cool. Oh, that is wild. Anyway, you need a lot of gravity to bend light enough for us to measure it. But it is gravity that makes light bend. The same gravity that holds you and me on the Earth, it's the same gravity that our Earth makes.
So to sum up, light can be bent, bounced, absorbed, or pulled by gravity. But if none of that happens, light will go in a straight line. Like this.
Science.
Light can travel straight, light can move, and bounce or absorb when it hits a funky groove.
The light that bounces back is the color that we see.
Take a trip with me now and hold on tight. We're gonna bust a move with something called light, which travels in a straight line as you can plainly see, unless it hits something or is pulled by gravity. And this might be a surprise. When light hits something, it bounces back to our eyes. But some light is absorbed, as you probably know. White light contains all the colors of the rainbow. A red thing absorbs every color but that hue. Orange, yellow, green, indigo, violet, and blue. But the red light bounces back, and that's the color we see, whether it's a fire truck, a sweater, or a skin duck knee. Now hold on, because I'm not done yet. You know, light can bend if it goes through something wet. Look at this pencil and you'll have to agree. Light bends if it passes through a different density. Light can travel straight, light can bounce or absorb when it hits a funky groove.
The light that bounces back is the color that we see.
Light can travel straight, light can move, bend, bounce or absorb when it hits a funky groove.
The light that bounces back is the color that we see.
Light can travel straight, light can move, bend, bounce or absorb when it hits a funky groove.
The light that bounces back is the color that we see.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some waves of light to bend. I'll see you next time light bounces off of you and refracts through the lenses in my eyes. See ya. Hey. What?
Produced in association with Walt Disney Television.
Hey, are you listening to me?
Mike's in front of it, right there. Okay, rolling.
Ready? Hey, are you listening to me? Hey, are you listening to me?
Rolling.
Okay, how's that?
Okay, come. Look. That's good. Rolling.
Hey, pay attention.
Try it again.
How about throw this one, Bill? Oh, it's just so weird, man.
Okay.
Okay. Rolling.
Action.
It's like so weird, man.
Major funding for Bill Nye the Science Guy is provided by the National Science Foundation, supporting education and research in science, mathematics, and technology, and by the Corporation for Public Broadcasting, and by annual financial